In this lesson, we're going to look at the idea of an invariant point of a transformation. That is a point that is not moved by that transformation, it stays in the same place. We're also going to look at lines of invariant points and also invariant lines. We're going to look at how to calculate these for different transformations, and we're also going to look at how to describe the geometrical significance of these. So firstly, an invariant point is any point that doesn't change when you perform that transformation. So if the transformation was a reflection in the line y equals x, given there, then for example, the point 3, 3 is on the line y equals x. So in that reflection, 3, 3 is mapped onto itself, it doesn't move. So we could call 3, 3 an invariant point for that transformation. And it turns out that any point along that line would indeed be an invariant point. So that would be called a line of invariant points. If a transformation matrix M has got an invariant point, call that point R, then we can say that MR just equals R because the point is mapped onto itself. Now R is just the vector xy, so it's just a short way of saying it. So in 2 dimensions, R, it could be a coordinate xy or it could be the vector xy. In 3 dimensions, R could represent x, y, z. So it just depends how many dimensions there are as to what kind of vector that is. So we're going to find an invariant point for the matrix A. A is given as -1, 5, 2, -4. So because we know that invariant points satisfy this equation, MR equals R. Remember that R is just xy in 2 dimensions. So we can say that the matrix A multiplied by xy just gives xy. Those points are not moved, they stay in the same place. If we multiply out that left-hand side, we'll get -x plus 5y, and then that equals x on the right-hand side. And then we get 2x minus 4y, and that equals y on the right-hand side. I'm just going to rearrange both of those equations slightly. So both equations, when you rearrange those, give 5y equals 2x. So the first one actually becomes minus 2x equals 5y. We can rearrange that. The second one gives 2x minus 5y equals 0. Again, we can rearrange that. So it gives the same line twice. That tells us that actually any point along that line will be an invariant point, because that line is a line of invariant points for this transformation. So you could rewrite this, you could call it y equals 2/5 x if you wanted to. If we just want one invariant point, we could just choose any value of x and y that satisfies that. So any point that satisfies that, you might choose x equals 5, y equals 2, because subbing that in would give you 10 on both sides. So an invariant point for that matrix is 5, 2. And more generally, any point along the line 5y equals 2x or y equals 2/5 x would be an invariant point. So the idea of an invariant line is slightly more complicated because that is a line that doesn't change under the transformation. Let's consider the transformation y equals x again. Now we know that any point along that mirror line is an invariant point, so we know that that is a line of invariant points. But if we consider any line perpendicular to that, let's consider the line y equals -x, which would be going down that way. Now that line would actually get mapped onto itself under that reflection. It wouldn't change, it would still be the line y equals -x. So we could say that y equals -x is an invariant line. Okay, so a transformation matrix M has an invariant line in a direction of a particular vector v if mv equals lambda v, so some kind of multiple of v. In other words, the actual direction doesn't change, but the multiple of the direction might change a bit. Any point along that line changes, but it might move to another point on the line. So for example, in this here, this point here, for example, is being mapped onto that point there. Or this point here has been mapped onto that point there. So the individual points are all moving. This point here is mapped to that point there. So they're not invariant points because the actual points do move, but the line itself remains the same line. The direction of it, the direction vector v, stays the same. It just becomes a multiple. In this case, it looks as though the multiple is actually -1 because it's just reversed. So some transformations, we can consider how many invariant points they would have by thinking about the effect they have on the 2D plane. So for example, a rotation in 2D, if you think about which points would move and which points wouldn't in a rotation, you can see that actually a rotation only has one point that is invariant, and that is the centre of rotation. Every other point moves around it. A reflection has an infinite number of points all the way along the reflection line. They are all invariant points. And remember that lines perpendicular to the mirror line, they are invariant lines. So although the points along that line do move, the line itself will remain invariant. So if a transformation matrix has a set of invariant points that form a line, then that entire line is called a line of invariant points. Now, a line of invariant points is a specific kind of invariant line. It's a specific kind of invariant line where every point along that line remains in the same place. So a line of invariant points is still an invariant line. So MV would equal just V. So in other words, this is the case where lambda equals 1. So every point has stayed in the exact same place. So we're going to look at how to find an invariant line of a transformation. So invariant lines are not quite as easy to find as invariant points, because invariant points are mapped onto themselves, and we can just use the fact that the matrix times xy has to equal xy for those points. With invariant lines, although the overall line equation remains the same, individual points along the line might move to other points, so we can't use that method. What we're going to do instead is we're going to start with the matrix 5, 15, -2, 8. I'm going to look at what the new points would be after we had done this transformation. So we can say that if we were to do 5, 15, -2, -8 times any point xy, that will be mapped onto a new point. We're going to call that new point x dash y dash. Now, because we know the original points lie on a line, we know the original points satisfy the equation y equals mx. So rather than writing y in that first vector, we could write mx in that first vector instead. So we could rewrite the left-hand side to the matrix multiplied by x mx, and that equals the new points x dash y dash. So the left-hand side, when we expand that, is going to give us the image of the old points, which were on the line. Now, expanding that out is going to give us 5 times x and 15 times mx on the top. That's going to equal x dash. And it's going to give us -2 times x and -8 times mx, and that's going to equal y dash on the bottom. Expanding using matrix multiplication, that's the top row, that's the bottom row. Now we are looking for invariant lines. We are looking for points that started off on the line y equals mx and that are still on the line y equals mx after the transformation. So the new coordinates, x dash and y dash, also have to satisfy the same equation. That tells us that y dash has to equal m x dash. So we are going to substitute into y dash equals m x dash. We're going to put y dash as -2x -8 mx, and we're going to put x dash as being 5x plus 15 mx. Subbing those in there gives us -2x -8 mx equals m times 5x plus 15 mx. We can multiply all of that out, and then every term is going to have x's in. So in this question, after multiplying it out, we can also cancel out the x terms. That's going to leave us with -2 -8m equals 5m plus 15m squared. Take that over to one side, which gives us a quadratic. So that is going to give us 15m squared plus 13m plus 2 equals 0. That has got 2 roots. It factorises into 5m plus 1 and 3m plus 2 equals 0. So we're now at the point where we've got this quadratic. It's going to have two solutions. The two solutions are m is -1/5 or -2/3. That is telling us the invariant lines of the matrix are the two lines y equals -1/5 x and y equals -2/3 x. Notice that they both go through the origin in this case, and neither of those got plus c. So in this example, we're going to look at finding any lines of invariant points and also any invariant lines of the matrix 2, 1, 2, 3. So we know that lines of invariant points are just special kinds of invariant lines. So we'll start by finding the lines of invariant points, then we'll move on to the invariant lines afterwards. So invariant points are any point that is completely unchanged by the transformation. So they satisfy matrix times xy equals xy. We can find that by multiplying out the left-hand side. Now the left-hand side, that's going to give us 2x plus 1y for the top element and 2x plus 3y for the bottom element equals xy. So that top row tells us that 2x plus y equals x. The bottom row gives us that 2x plus 3y equals y. So rearranging each of those, the first one becomes x plus y equals 0. The second one becomes 2x plus 2y equals 0, which is just a multiple of the first one, x plus y equals 0. So we've got the same thing twice. What that tells us is that the line x plus y equals 0, or y equals minus x, if you want to rearrange it, is a line of invariant points. So every point along that line is invariant. So we can say y equals minus x is a line of invariant points. We're now going to look and see if we can find invariant lines. Now they are lines where individual points along that line may move, but overall the line remains the same. So for this one, we're going to need to do a transformation. 2, 1, 2, 3. We're going to apply it to all points x, y, except because we know that we're initially going to be looking at a line, we know that originally the line that these points are on is going to be of the form y equals mx plus c. So we can actually write x, and then instead of y, we can write mx plus c. Because we know that initially these points are all going to lie along a line. We want to see if they're still lying on a line after the transformation. So we're going to set this equal to x dash y dash. X dash y dash is just the notation for the new points after the transformation. So let's expand out that matrix there. So I've got 2 times x and 1 times mx plus c. So that is 2x plus mx plus c. And then the bottom line, we've got 2x plus 3mx plus 3c. Now, if those points are on an invariant line, then they will have started on the line y equals mx plus c, and they will still be on the line y equals mx plus c after this transformation. So that tells us that the new coordinates, x dash y dash, will also have the same relationship. Y dash will have to equal x dash plus c. So I'm just going to substitute in the expression that we got for y dash. So we got that y dash was 2x plus 3mx plus 3c. That's y dash equals m, and then the expression we got for x dash was 2x plus mx plus c plus c. So expanding that out gives us 2x plus 3mx plus 3c equals 2mx plus m squared x plus mc plus c. So this is a little bit more complicated than the one that we had before, because we are now considering lines that don't go through the origins. They've got a plus c as well. So to simplify this, we're going to compare coefficients. We're going to start by just looking at the coefficients of x. So compare the coefficients we're going to take just the terms that have got an x in. So those terms are 2x, 3mx, 2mx, and m squared x. So those terms there, I've got 2x plus 3mx equals 2mx plus m squared x. So now all of those terms have an x in, so we can cancel the x's out. That's going to give us 2 plus 3m equals 2m plus m squared. Taking that all over to one side will give us the quadratic m squared minus m minus 2 equals 0. So we can factorise that to m minus 2 and m minus 1 plus 1 equals 0. So the two m values that we've got, the two values for the gradients of these invariant lines, are positive 2 and negative 1. So we're going to see what values of c would go with those m values in each equation. So I'm now going to go back to the step where I compared the coefficients, and I'm going to now take the terms that have a constant. So 3c, mc, and c. So from there, I can see that 3c equals mc plus c, or 2c equals mc. I'm going to substitute in each of the m values that I got earlier. So firstly, let's substitute in m equals 2. So substituting in m equals 2 gives me 2c equals 2c. That might seem like a really pointless thing to say, because that just gives me c equals c, but that's actually really helpful, because that means that is true for any value of c. So that tells me that y equals 2x plus c is true for any, that will be an invariant line for any value of c. Any constant that we put in there will be an invariant line. We now go back and look at what happens to the other m value, m equals minus 1. Put that into 2c equals mc. So we get 2c equals negative 1c, negative c. That gives us 3c equals 0, or c equals 0. That is only true for that one value, so only c equals 0. So that tells us that y equals minus, so minus 1x, plus 0 will be the other invariant line. So whereas we had a family of invariant lines for the first one, y equals 2x plus any value of c, we've also got a single invariant line, y equals minus x. And you will notice, if you look back at the original calculation we did, we had already found y equals minus x. That was the line of invariant points. That was a special case. So it's come up again when we were looking for general invariant lines, but we've also found that second family of invariant lines, y equals 2x plus c. So we're now going to look at finding the invariant points and the invariant lines of matrix X. So remember, an invariant point is any point that satisfies the equation the matrix multiplied by xy equals xy. So if we expand out that top line, I'm going to get minus x plus y equals x. Expand the second line, we're going to get minus 4x plus 3y equals y. The first equation gives us y equals 2x. The second equation is going to give us minus 4x equals minus 2y, which also simplifies to y equals 2x. So we've got that same equation twice. That telling us that there is an entire line of invariant points at y equals 2x. Every point along the line y equals 2x is invariant under the transformation. Right, we're now going to look for any invariant lines. So invariant lines are found by calculating the matrix multiplied by a general line, which is x, mx plus c, and finding the image points x dash, y dash. So multiplying out the matrix multiplied by that initial line, we end up with minus x plus mx plus c. And then we get on the bottom line minus 4x plus x plus 3c. So we are looking for lines that are unchanged by the transformation. So initially they were of the form y equals mx plus c, and after the transformation they are still in that form, y dash equals m x dash c. So we're going to multiply, we're going to substitute in y dash, which we found to be minus 4x plus 3mx plus 3c equals m times the expression we got for x dash, which was minus x plus mx plus c plus a c. So expanding that out, minus 4x plus 3mx plus 3c equals minus mx plus m squared x plus mc plus c. Okay, so as before, we're to compare coefficients. We're just going to take out the terms that have got an x in. That leads us to minus 4x plus 3mx equals minus mx plus m squared x. Cancelling out the x's gives us minus 4 plus 3m equals minus m plus m squared, or m squared minus 4m plus 4 equals 0. So that will factorise. That is actually m minus 2 squared. Leading us just to m equals 2. So we can see that the only gradient we've actually got there is m equals 2. We already found that y equals 2x was a line of invariant points. Let's just look and see if we can find any others with other c values. So if we just take the constants from the line we had there, 3c, mc and c. So we've got 3c equals mc plus c. So we've got 2c equals mc. If we substitute in the m equals 2 that we just found, we end up with 2c equals 2c, or c equals c. So that is true for any value of c. So you might think, well, does that contradict what we found earlier? It doesn't. We found earlier that the line y equals 2x was a special kind of invariant line. It was a line of invariant points. We've now found that any line of the form y equals 2x plus c will be an invariant line. Not necessarily a line of invariant points. The only line of invariant points is the line where c equals 0. Any other point with any other c value, any other line, with another c value will be an invariant line. So in this question here, we're just going to look at the geometrical interpretation of the line of invariant points and the invariant lines. So you can work through the same process that we did on the previous two examples to find those. I'm just going to give those here. So y equals minus 2x was a line of invariant points. Of this matrix. That can be found by doing the matrix times xy equals xy. By then using the process to find any other invariant lines, we will also find that y equals a half x plus c, where c is any constant, is an invariant line. And so there's an infinite number of invariant lines, y equals a half x plus any value of c. And the question is, what is the geometrical interpretation of this? Well, you may recognise this, or you may be able to calculate this using the transformations that we looked at previously. This transformation is actually a reflection in the line y equals minus 2x. So if we just do a quick sketch of that. That's the line y equals minus 2x. You'll see that if you are doing a reflection in that line, any point along that line will indeed be invariant. It will stay in the same place. However, y equals a half x, any line with that gradient will be perpendicular to the mirror line because it's the gradient is the negative reciprocal of minus 2. So any line going at 90 degrees to the mirror line with any y-intercept, any c value, that will be an invariant line because that line will get mapped onto itself. The individual points on the line will move to other points on the line, but overall they will stay in the same place. So the geometrical interpretation of that is that any reflection will have a line of invariant points as its mirror line, and any perpendicular lines to that mirror line will be an invariant line. So now please complete exercise 8C on page 180.